All right, guys, you're doing great. This is the fourth of 5 mini videos meant to guide you through Kinetics, the Chapter 14 material in the TRO textbook that is no longer a part of Chem 121's curriculum, but that you may not have gotten if you happen to take Chem 120 earlier than last semester. So, what we're going to look at in this video is how we get a picture of what's going on at the microscopic level based on how a rate law is built. Essentially, what it is that we can learn about the reaction on the basis of the dependence that we're seeing just from actual data. So for example, if I have a reaction like the one we studied, the 2H2O2 yielding 2H2O and O2, that decomposition that we discussed at the end of the last video, reactions like this don't tend to happen cleanly in just one shot. In fact, if you think a little bit about what H2O2 looks like, it's an H bound to an O, which is bound to an O, which is bound to another H. It's kind of hard to imagine geometrically how two of those molecules could strike each other and in one shot generate for you a water and another water and an oxygen molecule. It's very challenging to picture how that would work. There'd have to be at least a couple of intermediate steps in there. And so those intermediate steps, those elementary steps that can take place one at a time, make up what we refer to as a reaction mechanism. This will be a big thing for you in organic chemistry, looking at the kinds of things that can happen in one easy shot. Here's an example mechanism for this reaction. We might instead think that the H2O2 starts by splitting into a pair of OH radicals. And I want you to notice on that blue substance right there, you don't see a minus sign. If that was hydroxide, this would actually be a redox reaction because we'd have had 2 electrons get transferred to the H2O2 in the course of it breaking. This is instead the molecule splitting evenly in half, and so it results in 2 very high energy species called radicals that don't have octets at this point. They actually have an odd number of electrons around that O. As such, it's very reactive, and so what you might expect is that it will react with something nearby. Now, one thing it could easily do is those 2 radicals could come back together and remake H2O2, but that's no fun. What if instead it attacked another H2O2? And in this case, maybe the OH grabs one of the H's on the end of the H2O2, turning the radical into a water molecule, and leaving behind the H on the far side of the original H2O2 and the other 2 oxygens, making this HO2 radical. Of course, that's not going to be terribly stable either, but if that interacts with the other OH that we made, the result would then be to make water and oxygen. And I want to make sure we're very clear on one thing because students always freak out on me just a little bit when we do mechanisms. I am providing this to you. I am not reading this off and saying, oh, clearly you should be able to come up with this just off the top of your head. Admittedly, we're going to do a little practice with that in a moment, but right now I'm saying here's an example of how this might look. 3 steps that get us from an H2O2 molecule intact to our final products. And so once we've got this sort of mechanism, there's a little bit of terminology I want to make you familiar with. We classify these based on how many molecules need to collide for them to occur. And this ends up being really important because what we're going to see later is that one of these steps is going to actually explain our rate law very, very nicely because it's molecularity. The number of molecules involved and the specific molecules involved is going to be just right for what we're looking for. The words we use here for step 1, for example, is that it's unimolecular. In other words, that H2O2 doesn't need to collide with any other molecule for that to happen. Now, it might need to collide with something, molecule, wall of the container, who knows what. It would have to do something in all likelihood to get the energy to split itself in half, but it doesn't depend on the concentration of anything else around it in order for that to occur. Steps 2 and 3, by contrast, are bimolecular. They will depend on the concentrations of both. Their rates, at least, will depend on the concentrations of both species present there. Not just the H2O2, but also the radical. Or down at the bottom, both radicals. They'll both depend on that. I want you to think for just a little bit, and there will be an essay question on the Canvas quiz, about why it is that termolecular, that is 3 molecule steps, are exceedingly rare in mechanisms. Why would we tend to avoid them at all costs? I want you to think about that and write me a little something in there. We'll see if you can wrap your mind around it. Now, for a mechanism to be reasonable, it has to do 2 things for us. First off, Rather obviously, it has to add up to the full reaction. So take a note here. If I look at just the things that are in red, what you're observing are the reactants and products of the reaction itself. Two H2O2s, one of which cleaves itself in half to make the radicals that start the process, one of which then gets attacked by one of those radicals. Those are your reactant molecules. On the far side, the three red things are your two waters made in steps 2 and 3, and the O2 that's formed at the very end after HO2 loses its other H. Now, with all of that put together, we can see that what we get from the red is the full reaction. And notice how everything blue and green cancels out. The two OH radicals I made end up attacking two different things and getting consumed. The HO2 that I make in step 2 gets consumed immediately in step 3. We call things that are formed and then destroyed in the course of a reaction intermediates. They tend to be high energy, they tend to be things that have incomplete octets, they tend to be very reactive, and that's why we don't see them at the end anymore. They do something and become something else. If you ever see the opposite of this, something that appears at the beginning and is remade at the end so that it doesn't actually end up being part of the final equation, the word we have for that, and we're going to talk about it in the last video a little bit, is a catalyst. And you'll read more about that intro. We'll talk more in a later video. The other thing that the rate law must do in order to be reasonable, the rate mechanism must do, is that it has to agree with your rate law. And again, what the heck does that mean? Well, I'm going to use a quick visual aid for this, and it's one that I used to encounter on a somewhat regular basis, and that I'm happy not to anymore, and it's the Bay Bridge toll plaza and metering lights. If you've ever made a trip from the East Bay over to San Francisco or vice versa, especially at rush hour, you may be very conscious of the fact that the speed at which you can make that trip, the amount of time it will take you to get there, is incredibly dependent on how the toll plaza is. In fact, my own fiancée doesn't deal with the Bay Area or the Bay Bridge toll plaza. She deals with the San Mateo Bridge, but she works a funky schedule that leads to me teaching night classes specifically to avoid this sort of junk. So it is what we would term in kinetics terms a rate determining step. It is the slowest step, it is the bottleneck, it is the thing that when it gets jammed up, you can't go any faster than that. And so what we want to see, if we know what the rate law is a mechanism that has a slowest step that looks like our rate law. So in your work after the last one, you may have determined, and if you didn't, here it is, enjoy, the rate law for this reaction. You would have determined from the data provided that it was in fact a first order rate law, that largely coming from the observation that the half-life didn't change. Now, if it is a first order rate law and I look at these steps, the first thing I notice is that step number 1 depends only on the concentration of H2O2 and the number of H2O2 cleavings that occur per second is not going to be dependent in any unusual way on how much H2O2 I have. If there's a 10% chance that any molecule does it at a certain time, then if I double the number of H2O2s, I will double the number of those events that I see. And so it makes the most sense for that first step to be my slow one, rather than the other two. To give you an idea of what this might look like if it was one of the other steps, I want to take you through something known as the steady state approximation, so that we can see how that would actually work out, how it is you would, how the rate law might look if, for instance, the second step was the slow one. In the event that the first step was, let's say, a fast equilibrium between H2O2 and OH, because we know if I make the OH, it's not going to last for terribly long. If we assume that's a fast equilibrium and that the second step is the one that goes slowly, let's see what happens here. If I try to write a rate law based on this, what I'm going to come up with is my rate being equal to a K, we'll call it K2 since it's for the second step, times H2O2's concentration, but also times this hydroxyl radical's concentration. Note that this is going to be involved. The more of that I have, the more of this reaction can occur. Couple problems though. First off, the amount of this I have is extremely dependent on that equilibrium. And number two, I can't have this here because I can't learn that from an actual bit of data collection. I don't have a way of varying the amount of hydroxyl radical I have individually. That's, again, not hydroxide ion. It's a radical. It's an unstable species. I can't just say, okay, let's double its concentration and see the effect it has. I need to figure out how this affects the rest of the rate law. So what I'm going to do is use the equilibrium to destroy it, to get it out of my equation. And so what I'm going to do is look at the equilibrium I have up here at the top and recognize that for my forward reaction, I can write a rate law for it. For any elementary step, I can essentially follow this law of mass action. So for the forward reaction, like we saw before, I would expect that the rate would be equal to K times the H2O2 concentration. For the reverse reaction, I would expect the rate to be equal to K to the minus 1 times this hydroxyl radical concentration squared. Because in order for an H2O2 to form from my hydroxyl radicals, two of them have to find each other. And so if I knock the concentration down by a factor of 2, not only does that mean I have half as many hydroxyls running around in the first place, but they also have half as many partners to bang into. So it's kind of a double whammy. And it ends up manifesting itself this way mathematically. I should have made that K1 up here. Now, if this is at equilibrium, what that means is that these two expressions are equal to each other because the forward and reverse rates would be canceling each other out. We're going to learn a lot more about that moving forward in this class. But if that's the case, I can write this equation now. K1 times my hydrogen peroxide concentration equals K minus 1 times hydroxyl squared. And what I want to do is solve for hydroxyl so that I can replace it in here and get rid of it. And so to do that, we're going to divide both sides by K minus 1, and then I'm going to take the square root of the whole dang thing, and that's going to knock this guy out. And so now this can go back in for that. And the result here is that I end up with the following new rate law for my initial reaction. It's now going to be K2 times H2O2 concentration times all of this. So square root of K1 over K to the minus 1 and H2O2 also under the square root. So that's to the 1/2 power. It actually results in some pretty wild looking reaction kinetics that we haven't really discussed yet. But this, and this can all come together to form a new K for the reaction. But that times that gives me H2O2 to the 3/2. So there are some other options out there. This can get a great deal more complex as we go along, but I just want to show you that there is a way to deal with it if you end up with intermediates in your rate limiting step. However, for our purposes, the reaction we're dealing with doesn't act this way, and it's worth returning to the original slide to examine why that might be the case. The original slide here shows us as well that the first step is taking something very, very stable and making a very unstable thing out of it. You might expect that to be a difficult thing to do. If it's a reasonably strong bond, that's going to be hard. That's going to happen very rarely. On the other hand, the other two reactions have high energy reaction intermediates as their reactants. And so odds are pretty good that those are going to be very, very fast, because once I make OH, it kind of looks at itself in the mirror and says, I shouldn't be, boom, and reacts to form something. It's going to attack something nearby. Maybe the other OH, maybe one of the H2O2 molecules, whatever's around. At the end of the day, this one also makes more sense for that reason. But the be-all and end-all of this really is the kinetics. Does it match the rate law that you've actually gotten from data? So I'm going to ask you to try something out yourself here, and this is going to be basically where this video ends, but I'm going to ask you to try surmising a possible two-step mechanism for the reaction I'm showing here, NO2 plus CO yielding NO plus CO2. The main thing I want you to bear in mind is that the rate law for this reaction is second order in NO2, and that the rate is independent, in other words, zero order for CO. So consider what that means your rate limiting step should look like, and see if you can come up with a reaction mechanism, a pair of reactions that give you that particular behavior. Bear in mind, you might make some really weird looking substances that don't actually exist in nature. That's fine. They're intermediates. They're going to get destroyed anyway. Take a whack at it, put it into the Canvas quiz, and then come back and meet me here when we talk about how temperature and reaction energy can affect the rate of a chemical reaction.